Okay, so the photoelectric effect is pretty simple. What they observed was you would have a metal plate, it had electrons on it. When they hit it with light, electrons would shoot off. So the intensity, which is like the amount of light hitting the plate, would increase the amount of electrons that were ejected, but did not increase the velocity the electrons would leave the plate with. What they found was that a much less intense light, but with a higher frequency, would increase the electrons, which is not what they would expect, because the model they were using at the time had the energy from light being tied to waves, and it didn't matter what the frequency was, or what the wavelength was. So they kind of had this little problem where two things didn't make sense. So the energy of the particles leaving the plate could be described like a particle. So E was so it was an equation that involved the mass, or the velocity of the particle and the mass, which was constant because they were all electrons. So they wanted to solve for the energy that was these photons hitting the plate. So it was solved by Einstein using the work of a guy named Max Planck. And Planck is the one who came up with quantization. So what he said is that energy is not infinitely divisible, but it is quantized and exists in some sort of minimum unit called Planck energy. Einstein applied this to light, saying that light must exist in some minimum unit, which he wound up calling a photon. So there's one thing that Planck said, and he said that the energy of light could be described using this formula, and this was a constant. And this was the frequency. So a frequency is like, if it's traveling in waves, you're going to have this oscillating pattern. The length between the two peaks is the wavelength. The number of peaks that pass in like a set amount of time is called the frequency. So if you have, 100 wavelengths that pass in 1 second, then that's going to tell you your frequency. So what we're having is some particles that are behaving like particles, which are the electrons, and then light, which they thought was a wave, is also behaving like a particle. So, how to explain? So if more or tighter wavelengths increase the speed out, then they know that there's some connection between wavelength and frequency and energy. And that came to Einstein's work, which is c for the speed of light equals wavelength and frequency, which they're going to rewrite to be like, because they're trying to figure out how to factor frequency into an equation for energy. So they're just going to say that frequency equals speed of light over the wavelength, rewrite that. So now they factored energy to not involve frequency, but to involve wavelength, which is what they saw in the photoelectric effect. And then they'll do this whole thing, and they're just going to say that the energy of the photon is equal to this. And in the entire energy equation, they're going to say that there's some energy leaving, which is again the photoelectrons leaving the plate, and it's connected to the frequency of the light hitting the plate, and the reason the frequency had to matter was because there was some minimum threshold to meet before ejection happened. So it's just some energy holding electrons to the plate. Once you beat that, they shoot off. So this was the start of the wave energy duality idea, so that light activates as a particle, I messed that up. It's wave-particle duality. So it's kind of a simple idea, but it's also backwards thinking. Okay. So I'll just ask you guys, if we're increasing the wavelength, are we increasing the speed that the particles leave at? No. Yeah. And if you're increasing the intensity of light, are you increasing the speed that they leave at? No. The intensity didn't matter. It's the whole point. All right, cool.